classical physics does not predict.
Oh, question.
Yes?
With the black box radiation?
Black body.
Huh?
Black body radiation. I thought, sorry, I heard you say black belt.
Sorry, box. What did happen to the radiation when you like turned up, changed the temperature? That graph?
As you change, yeah, you get that graph. The difference is if you turn the temperature, so you get it at a set temperature, you look at the radiation coming out at various frequencies. You can turn up the temperature, and what happens is, I'll leave that side of it. The peak will start to change. So right now, and this is how you get an idea of the temperature of stars, because this peak right here peaks at a particular temperature, and then as the temperature increases, the peak shifts one way or the other.
And what causes that? That's the radiation level? Or what is that graph? The wave?
I had it as intensity versus wavelength, so it's basically how, if it were visible light, it would be how bright it is.
So the wavelength of the radiation?
Yes, that's coming out of the hole. Other questions? All right. The next big chink in the armor is the photoelectric effect. So you have some sort of surface here, a metal, and you shine light on it. And then you have a detector over here. And so as the light hits it, in some situations, an electron, basically there's enough energy, to make the electron get ripped out of the atom. The electron shoots up here and you measure a current. This is the essence of the measurement. So if I had a light here, if I turn the light up, what would you expect to happen?
More particles, more electrons?
Yeah, that would be expected. And sometimes that works and sometimes that doesn't. What they found is that light hitting this, there's some threshold frequency. I don't quite remember, threshold, 2 H's? Is it threshold, or is it just that word in the 1 H? Any idea? All right, we'll stick with 1 H for the moment. That there's a threshold frequency that if you are above that threshold frequency, then that works. You will get electrons ejected, and then more light, more electrons. But if you're below that frequency, that threshold frequency, it doesn't matter how bright the light is, you aren't getting anything ejected off of it. So below the threshold, did you find it?
It's one.
One, okay. Below the threshold, that no electrons ejected. Well, this causes problems here. Because if you look at the physics of waves, think about again the battle rope, there's definitely more energy associated with more frequency. Try that one again. There's more energy involved in a greater amplitude, because a brighter light just means a larger amplitude. I mean, if you're doing a battle rope at a certain frequency, if you made your strokes larger, if you went larger, you would get a larger amplitude, and it takes more work to do it, because if you're maintaining the same frequency, you have to do it a little bit faster, because you have more distance to cover. But there's definitely solid evidence that light is a wave. Because if I took the double slit experiment, I have some light source over here, and I have light waves coming in. Light waves are going to go through these two slits. And you see that there's points where the two light waves are gonna cross each other. If I have two peaks crossing each other, let's flash back to 151, what is that called?
It's not disruptive versus
Okay,
disruptive interference or something.
which kind?
Disruptive interference or constructive
Good,
interference.
constructive. It's constructive interference. However, if I look at the point where one's peaking and one is at the bottom, like right here, you're closer with the first one.
Destructive.
Say it again?
Destructive.
Yep, destructive interference. So what I would expect to see if light is a wave is if I had a screen over here, I would have a really bright spot in the middle, and then I'd have a less bright spot, and then a less bright spot, but I have these dark spots in there. And that's exactly what you see. Now there's something also known as single slit diffraction, and you can see it a little bit if you put your fingers together and you've got a little crack there. If you hold it up to the light and look really close, you've got these little dark bands going across. That's looking through the crack right there. Now some people's fingers don't do that. If you split it apart, you aren't going to see it. It needs to be a narrow slit. You see the little dark bands?
I think my fingers are too fat.
What was that?
I think my fingers are too fat.
That's possible. I know some people don't have that little crack right there, and some people do.
Like this.
So you have your fingers like that, and there's in some hands, and you get a small little slit right through there. And there's these little dark bands that you would see.
Yeah.
You see them?
Yeah.
Okay, we got at least one person in here.
The guy who wears glasses.
What's that?
The guy who wears glasses.
Maybe that's the secret.
Just wear glasses. Just wear glasses.
Oh.
That's the secret.
Okay. Anyway, that's known as single slit diffraction. I remember seeing that as a kid and thinking, I sort of imagined those were little hairs that I just couldn't see normally. But no, it's actually light interfering with itself. So we clearly have evidence, and this evidence has been around since the late 1600s? Somewhere in that area, so late 1600s, early 1700s. The evidence of light was a wave was a known fact. Yet, if light were a wave, I should just be, if no electrons are ejected, I just make the light brighter, and it should work. But it doesn't, if I'm below the threshold. So this is one of Einstein's contributions to physics. He established that there is a threshold frequency, and that if you think about it as, well, let's suppose I need a certain amount of energy to dislodge. I got some stuff on the floor and sort of stuck to the floor by Velcro to make it Velcro, and I need to dislodge it. If I throw something hard enough, I can make it break off, detach from the floor. If I throw it too soft, it's not going to break away. Well, a greater intensity of light means I'm just throwing more things at my target, and if it doesn't have enough energy to eject it, then it doesn't have enough energy. It doesn't matter how many balls I throw at my target, I'm not going to be able to rip it apart.
Question. Is there a different frequency threshold for depending on what the light is pointing at?
Yes. Yeah. Each material here would have its own threshold. And Einstein concludes that the energy of light is equal to Planck's constant, popping up again, times the frequency. So ejecting the electrons off of the surface here really does depend upon the frequency. All right. So Classical physics couldn't explain that, classical physics could not explain that. So we now branch into this idea that if we think about light as a small package, that it's not continuous, that light has little packets, which we now call photons. This gives this idea that light has sort of a particle quality to it. Well, light clearly has a wave aspect to it, but it also has a particle aspect to it. And so now we introduce Compton scattering. And now, and I know what you're thinking. You're going, hey, all this is great. Where's the math? Here's the math.
I was not thinking
Everyone else was, I'm assuming. I got a nod back there, or someone who just looked down. Got a sideways nod over there, so there's a general agreement. Compton scattering. Now, Compton scattering is I have an atom here. That's my nucleus. I got electrons zipping around here, and I shine light at it. When light hits the nucleus, if it's high enough frequency, as we know, an electron is going to go zipping off, and the light that comes out should be at a lower frequency. This whole idea that if you think of light as a particle, light comes in, some of the energy goes to an electron going shooting off, and the remaining light that's coming out should be coming out at a lower frequency, in other words, larger wavelength. We are going to simplify the drawing. When you're talking about light as a particle, you typically draw it as a wavy line. So I've got this wavy line coming in. I have an electron, which we will assume is at rest, especially considering something coming out at the speed of light. So this is my before. And afterwards, my electron goes shooting off at, I did not label that angle, I labeled the next one. All right. And then light comes back at some angle there. So we're going to do a little conservation of momentum. If light truly behaves like a particle at times, then we should be able to use our what we know about momentum. So what do you know about momentum in a collision?
Depends on the collision.
How so?
If it like, what was the word?
There's a perfect, imperfect.
Inelastic and elastic.
Okay, so combine those words, that deals with the kinetic energy.
And there's a third one, right?
There's perfectly elastic, perfectly inelastic, and imperfect, at least in my vocabulary. But that depends upon what happens with kinetic energy. Now, we are going to assume that this is a perfectly elastic collision. Why? Because we're dealing with some fundamental particles here. Friction does not exist at this level. There's no sound either. Pardon?
Impulse. Very impulsion.
Impulse is a D to key word, but I need something fleshed out a little bit more. This explains some of that last test of last semester. All right, so let's talk about this. A perfectly elastic collision. What does that mean?
That's going to perfectly bounce off each other.
Say it again.
They're going to perfectly bounce off each other.
They will, but perfectly elastic. Imperfect, they bounce off each other too.
But no energy is lost.
More specifically,
No. No
Kinetic
kinetic
energy.
energy.
there we go. That's the perfectly elastic, and then the collision.
There's collision. No, what kind of is lost?
There we go. Momentum's conserved. That's what I was shooting for a couple minutes ago. So perfectly elastic, collision so delta K is equal to 0 and delta P equals 0. All right. My momentum before equals momentum afterwards. So we're not dealing with relativistic effects here. So I'm sorry. I know it'd be a lot of fun to throw an extra couple of letters into it, but not today. What is the formula for momentum?
P equals mv.
Except, what mass am I using for the photon?
The mass of an electron.
Well, I have mass of an electron, but that's not the mass of the photon.
You just made it up.
No.
One.
Is it H?
Pardon?
H?
It is not H. H will pop into it though. All right. So I know energy is equal to mc squared. Now, if we're talking about a particle here, you know, the rocket ship, whatever you happen to have, this mass here is the rest mass times the Lorentz factor. That this would be gamma m sub naught if we're talking about something much more physical. But light doesn't have a rest mass, but it does have a mass equivalent. That the mass of light would be equal to E over c squared. And this is sort of a mass equivalent of light. I know that that's the formula, so the momentum of the light is equal to mv. So that would be E over c squared is the sort of the mass equivalent times the speed of light. And what we're left with is just E over c. So the momentum of light, so this would be for the electron, and then the momentum of light. And the symbol we use for light is, yes, it's the same symbol we use for the Lorentz factor. But Lorentz factor not involved here is equal to, the magnitude's equal to the energy of light divided by c, the speed. And energy of light, as we figured out from the photoelectric effect, is h times the frequency over c.
So that P gamma stands for light?
P is momentum, and the gamma is a symbol for whatever electromagnetic wave it is, light. Do recognize that in physics, when we say light, we don't necessarily mean visible light. It can be frequency of light that we don't see or see. All right, momentum is conserved. So my initial momentum is all light. The electron we're assuming is at rest relative to the speed of light. And then afterwards, it is shooting off at some speed. Let's say, I'll just label it as V. This is going to have some frequency, making sure I did F sub F. So it comes in at some initial frequency, it goes out at some final frequency, and this is some speed p. Well, so initial momentum equals final momentum. Well, my initial momentum, I just have one. That's my initial momentum. My final momentum is the sum of those two. Well, I know the light is shooting off in that direction right there, so that's going to be the momentum final of the light. And my electron shooting off in that direction. And that would be the momentum final of the electron. And this angle right here, theta. All right, time to use some of those math skills. What does this side equal in terms of the other three things?
Oh, pi squared. That's an I, right?
Yeah.
And then pf gamma plus df gamma squared.
Oh, you're stopping there?
What's the constant? I don't know.
No, not just plus the constant. I know some of you have had drink. This works if theta were 90 degrees, yes. But theta's not 90 degrees necessarily.
So cosine something.
Yeah. Law of cosines. The more generalized form of the Pythagorean theorem. So if theta is 90 degrees, we have a right triangle. Cosine of 90 degrees is 0. This whole term drops out. We have the Pythagorean theorem. All right, let's plug in what we know.
Wait, what is pi again?
That's the initial momentum. That is going to be the h times the initial frequency divided by the speed of light. It's the momentum of the light that's coming in. And I wrote before there, let's make it official, after. So this is mass of the electron times the speed final of the electron, which is just v squared, is equal to my initial momentum, which is hf initial over c, all that squared, plus the final momentum of the photon, which is hf final over c squared, minus 2 times hf initial over c, hf final over c times the cosine of theta. All right. Questions up to here?
Is there a simpler form for that equation?
Oh, we're
We're working towards it.
working towards it.